Yeah, so remember the test. I'm going to send out the test Friday afternoon sometime, or I'll post it to Gradescope is what I mean. Not send it out because it's that thing I said of like once you access it, I'm writing the test to be like 90 minutes, but I'm just giving you like way more time than you need just in case there's like technical issues with like scanning and uploading and stuff. Although I've seen students in my office like finish their problem sets like boom, 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 picture, picture, do, boom, upload it in like 2 seconds. So it's probably not that hard. But if you have a, if you're having, I just want to give people plenty of time. So, and also so you don't just feel super rushed. And also when I used to give like sit down evening exams, I would write them to be 90 minutes, but I wouldn't kick students out. Like I would like let them stay pretty much as late. Well, we would start at like 6:30 and by about 9:30 or 10, I would start being like, all right, come on. You've like you're just getting diminishing returns and you're just tired and you're, so I wouldn't, so I would let students stay like longer than 2 hours or whatever. I didn't really force students to stop. So until I got to the point where I really wanted to go home. So I figured I'd give you about a similar window for this, but yeah, so that should be fine. And then, like I said, maybe before, you can use a note sheet like front and back of 1 page of notes. And so I would recommend between now and whenever you open the exam, sitting down and going over things and making a note sheet. Maybe different students, some students just write the concepts and formulas out. Some students like to write out some specific homework problem solutions or something, or do some new problems from the book, just to write them out, just to have example problems worked out on their sheet. So whatever you feel like is right for you. And then I will post it, yeah. So, okay, but I'll definitely let you know all the details when it gets to that time. Any other questions about the test? No? I guess it's one thing I should say, I'm surprised no one asked, is it is like a closed book, closed notes test where you can use a note sheet, but you can also use a calculator or even the Google graphing or search bar or Wolfram Alpha. If you want to do computations, I don't want I usually try to make problems where it's not so much about computing, where you're gonna have to compute ugly, hairy things, but even if I asked you to compute the angle between 2 vectors, I'd probably just ask for the cosine of the angle. I wouldn't even really care about the actual angle, because that's, you definitely would need a calculator if it's a weird angle. So you don't really need a calculator, but if you want to use stuff like that, that's fine. You're just not supposed to search for the question, and the answer, right? Stuff that's obviously not cool. So, okay. Yeah. All right. Anything else you guys want to talk about? No? Okay, so today we're moving forward, and this is stuff that's no longer on the first 2 tests, right? The stuff, basically we finished last class. The tangent plane stuff is the last thing that would be on the test. So this is new material, but it's connected to everything we've done so far in that specific way that math is kind of cumulative, So, so let's dive in and start thinking about the directional derivative. And we're gonna I'm gonna have you guys compile some data. But the way I want to think about it is, we know the derivative in the positive x direction, the positive y direction, right? I was talking to students in office hours this week, if you're looking at those contour maps and you want to think about the derivative, the partial x, you move due east, you move in the positive x direction. You want to think about the partial y, you move due north in the positive y direction. So we know, or we can find that we can find is better probably. We can find the derivative / instantaneous rate of change in the positive x direction. I guess I should say of a function. I would say of a function z equals f of x comma y in the positive x direction. That's just the partial x. Positive x direction, right? That's the f sub x. In the positive y direction, that's f sub y. But what if we wanted to move in some random direction? Like, what if I wanted to move away from my point in the direction of the vector 3i plus 4j or something like that, or 5i minus j, right? Because there's still a function and it's still changing, and you can still estimate rates of change, and you can still try to do an instantaneous rate of change. And by the way, this is given by, like when you had to estimate on the graph, it's like you could estimate a delta z change in the function over the change in x, or the change in the function over change in y, right? So, but what if we want to leave, I guess I should say this, at a point like a comma b, right? So we're leaving, what if we want to leave a comma b in a different direction? Like, say, I don't know, like 5i minus j or something like that, or negative 3i plus 4j, et cetera, right? So something like a completely different direction. And I claim we have the tools to do this. It's not that bad to compute, because you want to think of, right, like you're on the surface at this point, and you zoom in and it basically becomes this tangent plane, right? And so, and the tangent plane's oriented some direction, it's tilted a certain amount, oriented in some direction, right? And you can sort of say, okay, well, we know the partial x, if that's, remember, x-axis, y-axis, z-axis. We know the partial x would just be the slope in this direction. We know the partial y would be the slope in this direction. And so you can imagine following the plane in some other direction and finding the slope, right? It's not that bad. So let's do an example. So let's do just kind of a simple example, like our old stalwart, the paraboloid, the bowl shape. Let's just say at the point I picked was -1, 3. Okay, that's a point. Partial x, the f sub x is just 2x, right? And the f sub y is just 2y. It's not bad. And so in particular, the partial x at -1, 3 is -2, just plugging in the x equals -1. And the partial y at -1, 3 is 6, 2 times y. So that's what I'm saying. We know the slope. This is the slope in the positive x direction. If we leave that point in the positive x direction, if you think about the bowl shape, you could kind of guess this would be negative and this would be positive. Because just think about, like, right, we sort of said we get these concentric circles that get closer together in the, that's the contour map. And so if I'm at a point like this point right here, and yeah, say this is like height well, I guess this is height 10. So if I'm at this point right here and it's at like height 10, so say that's height 5, 10, 15, 20. Right, if I leave the contour going this way, I'm between the 5 and the 10 contour. So that's negative, it's going down. And if I leave the contour this way, I'm between the 10 and the 15 contour. So that's going up. Is that believable? It's instantaneous, right? It's just what's happening just at this point. Okay, so it's at least believable that these are the right derivatives. But again, now, what if I want to head off like in some other direction from this point? Well, we have a way of thinking about this, right? We know we can write down the tangent plane equation, or we can just use the differential. Either way you want to think about this. Like, so the tangent plane at -1, 3 is, well, we know, right? We know f of this point is 10. So we know that its height is 10. Right, I'm just doing -1 squared plus 3 squared. We get 10. And so we can write this down pretty easily. It's z minus 10 equals the partial x minus 2 times x minus -1 plus the partial y times y minus 3. Remember that? That's the kind of the general equation for the tangent plane where this is our point. The point on the surface is -1, 3, 10. The point on the surface. And this is the slope in the x direction, the slope in the y direction. Right? But I said also you could think about this as a differential, that these are like deltas or d's. Like we could rewrite this as, it's kind of what I was talking about last time, which is like, we're gonna think of this as dz is -2 dx plus 6 dy, because this really is a delta y. This really is a delta x. And this really is a delta z. And I'm using d's because I'm thinking about on the tangent plane. I'm thinking about differential because I'm like on the tangent plane. Right? This is on the tangent plane. Any questions? Anything I'm not explaining carefully? I guess because the way I'm thinking about it is the following. I'm thinking like, if we want to know the slope in a direction, we don't actually want to follow the surface. We want to follow the tangent plane. Because the surface curves away. But the tangent plane is nice and linear. It just go down in dimension. Think about if you want to know the derivative at a point, you look at the slope of the tangent line, not like you don't pick a point on the curve. You don't pick a second point on the curve because you get a secant line. You follow the tangent line instead. So I kind of want to think about it this way. This is like, this is true on the tangent plane. So if I want to go in the direction, like let's say 5i minus j, right? So let's leave -1, 3 in the 5i minus j direction and find the slope of the tangent plane in that direction, because that's really what we're looking at. That's what I mean by sort of the directional derivative, the derivative in that direction. Right? But if you think about it, so we're at this point, let me just draw this sort of schematically again in the xy plane. We're at the point -1, 3. We're at this point, but we want to leave in the direction. So like up here, I drew arrows directly to the right or directly up, right? Those are the partial x and partial y directions. But now I want to leave in some direction like that. That's like 5i minus j or something like that, right? So this is 5I minus j. This is the point -1, 3. And I guess what I'm saying is like, didn't draw that very well, but but like there is a delta x and a delta y here, or a dx. Dx is -1, dy is 5. Right? I'm just changing x by -1. If I'm going into 5I minus, wait, what did I just write? I switched x and y, sorry. dy is -1 and dx is 5, right? I change y by -1, I change x by 5. That's the direction we're headed. And so we can actually get the dz very easily, the change in z along the tangent plane, very easily just by using the differential right here, this formula. Right? So then dz is -2 times 5 plus 6 times -1. So that's actually -16. So again, what I'm saying is like, we're really thinking about being on the tangent plane now. We're thinking about being zoomed in on the tangent plane. If we start at a point and head to this other point, which is like over 5 in the x direction, -1 in the y direction, we end up at another point on the tangent plane. You have these 2 points on the tangent plane that are connected now. And I guess it's tilted way down because the change in z is actually -16 if I go in that direction. Does that make sense? Just follow the tangent plane. But what we really want is we want the slope. We want the slope in that direction. So what we really need is the change in z over the horizontal movement. When I say horizontal here, I mean x and y are horizontal and z is vertical. Right? Just we have to say that explicitly here, else it gets confusing. This is all horizontal movement, right? In terms of x and y. Z is vertical. It's kind of funny that like that horizontal movement is 2-dimensional and vertical movement is 1-dimensional in our 3D world. There's like an asymmetry between horizontal and vertical. I think it's also a thing that you can always tell north from south, but it's harder to tell east from west. I don't know. There's something we very easily orient ourselves in z direction. Well, that's actually not even. That's more on when you're looking at a map and you see up and down the current. Well, you're right. This is like an abstract quantity, but it like if you actually do pick a direction to leave, like then you'd get specific dx's and dy's, and you get a specific dz. Well, at a point, you're right. There is no dx and dy. It's like, I mean, you find. I guess I'm just putting this in the tangent plane equation. So this expression I'm just getting from like the partial derivatives, but at a point, this is the differential, but there's no specific dx dy because you're not actually leaving the point. If that's what you're. So I picked. So this is kind of a random choice. I picked 5I minus j as a direction to leave. And so I'm just saying that arrow is like go over 5 in the x direction, go down 1 in the y direction. And so that's, yeah, so this direction, so the direction is sort of like, in general, the direction, what I mean is like, let me just come over here. I think this is on the screen. It's like dx I plus dy j is the direction. That's sort of the direction vector. And so I just happen to pick a specific one just to try to compute it. But we want the slope, right? So we found the change in z along the tangent plane, but we want the slope. And so slope is rise over run. This is the rise. It's -16. So it's actually fall, I guess. And then the run is just the horizontal movement, the total amount of horizontal movement, right? Yeah, this is like, so we want slope, which is rise over run. This is the rise right here. What's the run? The run is the horizontal movement. But I went from this point to this point, basically, right? So what's the run? What's the horizontal movement? Again, X and Y are horizontal, Z is vertical. What do I mean when I say, how would you, what's the horizontal movement from that point to that point? Yeah, it's just the distance. It's the distance. This length right here is sort of the run part of the rise over run. So it's the distance between the 2 points. But it's really, and that really just becomes the length of this vector, right? So that's right. That's the change in position in the XY plane, or the distance traveled in the XY plane. And here, that's just the square root of 5 squared plus minus 1 squared equals the square root of 26. Okay, so that's the run. And so it's not like a super nice number, but we can say that like the rise over the run is this negative 16 over root 26. And that really is the slope in that direction. Switch the board so you can see this. So, right, again, if I leave, it's like here, if I leave in this direction, that's sort of the 5i minus j direction approximately, not exactly, but it is going down again, right? It's going down. It's going towards the center more of the bowl. So it's, the z is decreasing. So you expect a negative slope in that direction. Okay. And so here's the thing. I'm doing this sort of the long, hard way just to try to like do things from first principles. It's going to turn out there's a nice formula, but I kind of want us to discover it. I don't want us to just tell you what it is. But you just have to get used to the fact you're just computing a rise over a run. You're doing it along the tangent plane. You're picking a direction like 5i minus j. You're using the differential to compute the change in z. And then you use just the length of that vector you chose to compute the change in the horizontal movement, which is the run part of the rise over run. And then you just do the rise over run. So the slope, or really what we're going to call the directional derivative, in the direction 5i minus j is rise over run, which is minus 16 over the square root of 26, which is whatever that is. I don't know. It's about minus 3. Actually, I want to compute this because I'm going to want us to, I want you guys to find data, and I'm going to want us to plot that data. So negative 3.138, let's just round it to 3 digits. Negative 3.138. Okay, so that's the slope in that direction. I guess maybe that makes some sense. The slope in the positive x direction was minus 2. And this seems like it's a little more, sloped a little more down if you go that way, because you're going more towards the center of the bowl. So maybe plausible. Okay. So what I want us to do is I want us to compile some data. And let's just use this example at this point, but I want to pick a bunch of different directions and compute the slope in all those different directions. And I'll put this as a table. But I also want something to graph it against. Like I want to see how it's changing as we change our direction that we're pointing. So it's like again, we're on this ramp. A lot of times now I'm going to imagine you zoom in at this point on this surface and you're on this ramp. and you want the slope in all sorts of different directions, right? And so now we know the slope in 3 directions. We know the slope in the positive x direction, the positive y direction, and we know the slope in this direction. And I want us to compute it in a bunch of different directions and sort of plot that data. But we need to plot it against something. So let's plot it against angle. You know, like we're just kind of, it's almost like we have this little compass that's turning around and choosing a direction. And then we want the slope in that direction. But if we want to plot it against something, let's plot it against the angle, like just the angle it makes the positive x-axis, for example. So let's think about angle. Yeah, let's plot these slopes against angle, namely the angle with the positive x-axis. So what I mean is like, just because that's our reference angle, that's our 0 angle is positive x direction. What I mean is if we're at this point and we go in the 5i minus j direction, right? Then there's some angle that that makes with that axis right there, right? And how do we find that angle? You guys know? Yeah, I mean, there's a triangle here, right? There's a triangle with side 5, 1, but really, I guess, -1. That's really what we have, right? And so tangent of theta is -1/5. So theta is inverse tangent of -1/5. So let's see what that is. I don't know what that is. Let's use a calculator. Arctan -1/5. Let's say in degrees. Can I do in degrees? That was not what I wanted, but it doesn't matter because Google understood what I wanted. -11.3 degrees. Okay. So this is about, well, let me just do it. Let's see. Yeah, -11.3 is fine degrees. That's a reasonable guess for that degrees right there. Okay, so what I want you to do is I want to make a table. Let me make the table here. So this is about -11.3 degrees. So let's make a table. Let's pick a direction. We're doing this all for this specific example. Let's do the slope in that direction, the directional derivative. And then the angle that it makes with the positive x-axis. So the direction here was 5i minus j. The slope we got to be about -3.138. And the angle we got was -11.3 degrees. Does that make sense? Just because I want to understand what the pattern is. Like I want to understand how this changes as you sort of change the direction you're pointing. And that really means changing the angle you're pointing at. I claim there's a nice pattern if we actually plot this data. So I'm gonna plot like directional derivative versus angle. So what I want you guys to do in groups for maybe like 10 minutes or so is actually help me generate this table. Like I want you guys to pick directions, right? Everything, we're gonna use this. It's basically, if you think about it, once you pick a direction, the direction is like, this is the dxi plus dyj. And then the slope we just found is dz over the square root of dx squared plus dy squared, which in this example is -2dx plus 6dy over root dx squared plus dy squared, right? Does that make sense? That's kind of what we computed. That's how we got this numbers. This was the DZ, and this is the rise over run. Oops, sorry, this is rise over run. Does that make sense? So once you pick a direction, you just have to plug into this formula to get this number. And then you can find the angle using that inverse tangent thing. Does that make sense what I want you to do? So I want you to pick a bunch of different directions, try to pick a couple different ones and pointing in weird different ways. I'd like to collect as much data as possible. So I pick 5i minus j, you could do I plus j, you could do 3i plus 7j, you could do negative j, you could do whatever, right? And then I'll have you guys can come up and fill in this table. I'll just keep doing it. And then I can put that into Mathematica and plot it. I can type it in as you guys fill it in. Plot it, and I claim something nice is going to happen. May not be obvious, but I claim something interesting. It's going to happen. So, yeah, I'm just going to continue this table here. Like, let's see how many. We should get a lot of points here. We could put a lot of data here. Okay, so can we break into the same groups we've been in? And then you guys go to the boards and compute some of these, and then like come up here. As you compute them, send people up to fill in lines of this table. And then I'll type it into Mathematica as we go. So let's do that. Let's jump up, pick directions. We'll try to fill in this table. We can always do a second. Yeah, let's do it. Let's get up. Go, you guys start doing that. I'll have you guys generate data. I'll do more over here. I'll pause the recording.